Is likely to rain on Saturday. Second, there's an after-school environmental film tonight at 6. It did not show last night, and it will not show tomorrow night. It's called Who Killed the Electric Car? It's a semi-conspiracy theory, slightly tin hat, but frankly, factually accurate and kind of indisputable story about how we've had electric car technology for a long time, and the first time that we got ready to make them, we didn't actually make them after all. Kind of interesting story. Tonight at 6 p.m. You can find out why when you watch the movie. It's not that much of a conspiracy. Everybody kind of knows who made it and who decided. And it's just a question of, was there actually pressure from the petroleum world, and how much pressure, or whatever. If there are no other questions, we got to do this stuff now. Yesterday, did we talk about moderators and coolant?
Yeah.
A little.
So, we will have kind of a busy day. You copied this already, and now you're going to write on it a lot. You remember from yesterday, uranium-235 is the special stuff. Very rare in nature. You have to enrich that. Once you're up to 3 or 4%, you throw a neutron into the mix, and that promotes it to an unstable isotope, which will split. The nucleus will actually divide. You will make one atom into two different atoms. And in doing so, you release a lot of energy. You get a variety of radioactive products that are more radioactive than the fuel was. You got to be able to explain why. Uranium is a big old nucleus. You can stick neutrons all over the place. But when you break that into smaller nuclei, you cannot stick as many neutrons. In other words, the uranium can hold a lot of neutrons, but once you split it, the radioactive decay products cannot. So they're not going to split at the atomic level anymore, but they are going to emit neutrons. It's a very nasty type of radioactivity. And they're going to keep doing that for a long, long time. That sucks. Because neutrons are what starts more reactions. So once you start this, the chain reaction is unstoppable. The best you can do, please look up, is try to keep capturing neutrons. That's to moderate. If I didn't say that yesterday, you'll absolutely need this now. Moderation is the capture of neutrons to control the rate of the chain reaction. To control the rate of the chain reaction. Did you know if you control the rate, you control the heat, and that's pretty good. But I think you realize that all of that unstoppable continuous decay is going to give off heat. So the second thing you have to keep control of is that heat. Please look up. You got to have a coolant. Usually that's plain old water. You got to have something to take that heat away. So cold going in and hot coming out. That's the second thing you need to control. Control number one is the moderator. Usually it's boron. The control rods will slow or speed up, slow, speed up, slow, speed up the reaction. And the second thing you need is a constant supply of cold to take away the heat. That's called the coolant. Moderator to control the rate of the reaction, coolant to help you shed the heat so you don't overcook. Are there any questions at this point? Yes?
Where does boron Why is it used as a good moderator? Yeah.
Because every atom of boron can absorb, on average, 1 neutron without any continuing decay, so it won't give it back. You can make boron into boron plus neutron pretty easily. So as long as you've got huge rods of solid boron, they just go, they're like little sponges for neutrons. As long as you keep adding fresh boron, you can eat up all these neutrons. That make sense?
Yummy.
Anybody else? Who has a pressure cooker? Today's warm-up. Anybody have one in their house? So basically you put some water and some stuff in there, and then you like heat it up. And then what's that little thing on top of the pressure cooker? It's got a horrific name, so we're not going to get into that. Anybody know what it's actually called? I'm glad. It's the word for a male chicken. It's not rooster. And so that little thing, what does it do on a pressure cooker? Not exactly. Not exactly. Not exactly. It lets you vent pressure when the pressure gets too high. So who can tell me how a pressure cooker actually works? Like my beans take like 4 hours if I cook them this way, but only like 30 minutes if I cook them this way. It's magic. How does that work? Yeah?
Does it trap the steam which like heats up the water more or something? I'm not
That's exactly what it does. How does steam heat up the water more?
because it
Steam is
molecules
hot.
are moving faster.
Sort of.
It's
Yeah.
hotter
The
than
water makes the heat more hot, I think.
Kind of right, but kind of not. Yeah.
It increases the boiling point, so you can make the water hotter without like vaporizing it.
Right. The molecules carry more energy before they can leave as steam. It raises the boiling point of the water. Instead of boiling at 212, when it's got no place to go, that water gets to 250, 270, 290, and it just can't boil. You prevent the water from expanding into steam by keeping it under pressure. So it cooks your beans faster because it's hotter than boiling. It's a lot hotter than boiling. It's like 1,000 times hotter than boiling if you pressurize it enough. Everybody got that? So please look up. It's called a pressurized water reactor because you have super pressurized water, so it'll get super hot and it doesn't go into steam because it can't. It's very important that everybody sees something. I'm going to give you 2 passes on this, but you've got to look up for something. Remember that if we don't bring back cold, it melts. And if we don't take away the heat, it melts. And that's disastrous, like apocalypse time. So a nuclear reactor does 2 things at once. The reactor itself just makes heat. So once we leave the containment structure, things are very, very simple. Steam, turbine, electricity, no big deal. All the fancy engineering is to get this hot enough that it'll make steam. You have to get rid of the heat. Follow the red. You got to take this heat and make it into steam to make that into steam or hot water somewhere else. We have to take highly concentrated energy, expand that to still pretty good quality energy, and then expand that again to dissipate it to the environment. In order for that to work, you got to bring in cold to make sure this stays cold, to make sure this stays cold. Yeah?
Isn't there a lot like safer
I mean, safer and cheaper ways than using nuclear energy to produce steam power? Like, why do they still use?
This is debatable. So, the glory of this is after you've built one, they pay for themselves pretty soon, and then, like, nuclear energy is the cheapest per kilowatt. James, put away your cell phone. Is the cheapest per kilowatt of any energy source. By far the cheapest. Because there's one cost nobody's had to pay yet, which is handling the disposal forever. If you don't factor waste disposal, this is probably the cheapest electricity source. And yeah, there's a lot of ways to make steam, but you'll notice there's no CO2 here.
But there is the radioactivity and the uranium waste, right?
Shut up, liberal. Yeah, that's exactly right. And by the way, it all sounds really cheap because nobody's forecasting the bill that's in the mail. You're solving today's global warming issue by making an eternal hazardous toxic waste issue.
Whatever. That's for the future people.
Yeah, whatever, exactly, right. The future will appreciate us for not getting the global warming.
Yeah, right.
So watch me. There's this thing called counter-current flow. You bring the hot water down and the cold water up. Does anybody know why it's counter-current? Why do you bring the hot water this way and the cold water that way? Watch me. If you bring hot and cold together, they'll average at warm and then go away both warm. Does that make sense to everybody? Mm-hmm. But watch. If you go hot water this way and cold water that way, the hot gives up its heat. But if there's any heat left, that'll meet the coldest water, so there's still a gradient, right? And as the cold water heats up, it still meets the hottest water, so there's still a gradient. You get more temperature exchange if you go counter-current. Everybody understand what I mean by that? This is like barely above cold, but that's still good enough to help this very cold water coming in. And by the time that hot water is almost steam, that's pretty effing hot, but this is still hotter than that. That's why counter-current, okay? All these are counter-current. So you'll notice that you come in cold here and go out hot there. Actually, it's not counter-current. It should have been counter-current. I drew it sloppy. Might be. Extremely hot coolant goes through the heat exchanger to make steam, and now we're just making electricity the regular old way, steam, turbine, spinning, no big deal. Notice something that's very important. In this primary cycle, that's the only place you've got radioactivity. That's very important for everybody to visualize. On The Simpsons, they always put the radioactive symbol on this thing. Or they'll show the water going into the river and the three-eyed fish. Anybody seen that episode of The Simpsons? That's bogus. Like, Matt Groening is actually a really, really, really serious good scientist, and I've always been sort of surprised by that. He's trying to convey to the public the fear of the radioactivity. He just did it in the wrong way. Where that hot water goes out, there's nothing radioactive. You can go surfing here every day, that's fine. The reason they make this thing called a containment structure is so that any radioactivity, even if it leaks, will be limited to the containment structure itself. The only thing that leaves is steam that is clean water heated by a pipe full of radioactive stuff. And if you make the pipe right, and you switch the water often enough, there shouldn't be any radioactivity traveling there. Everybody got all that? Primary cycle is radioactive. Coolant heats up, cools down, heats up, cools down. That's the primary cycle. It is radioactive. Secondary cycle goes from water, which is not radioactive, to steam, which is still not radioactive. That steam spins a turbine, you condense it. Everybody knows how a condenser works. You take a cold soda into the shower and the steam condenses the droplets under cold soda, takes away the heat from the steam. Everybody know that? Okay. I'm going to go take a very steamy shower and I bring in a cold soda because I'm just like drinking cold soda and I leave it and I take a shower and I make a bunch of steam in the bathroom. All that steam will condense as water droplets. That's condensation. You understand that? I've heated up my Coke and I've cooled off some steam into droplets. Right? So you bring in your cold soda into your steamy sauna, and that will condense into droplets, taking away the heat. You can spray that into the air to make clouds of not radioactive steam, or you can dump that into rivers or ocean.
Why don't they harness that steam coming out of the cooling tower too?
Because there's no such thing as a free lunch, and you can only get so much energy out of these translations, right? You're going from really high quality to pretty high quality. That's still pressurized steam, but at some point we've got to get rid of the heat. You can't have heat going back into the system. So someplace you've got to let it go.
Gotta let it go.
My son keeps singing the song from Frozen. I wish I hadn't said that. There's like apparently some like suburban or rural couple that made all the music for that movie, and now they're like gazillionaires. And I hate that.
I saw a CD that said like the voice of Elsa in Frozen at Starbucks, just on the counter. Some
Far out. Yeah, I don't know who did the actual singing. I know there's coincidentally some like teenager who looks just like her who's made an exceptional career of like guest appearing as a model of her in the real world, like walking around, hi, I'm Elsa. And they're like, oh, she's so pretty. And it looks just like her. Okay. But the people who wrote the music, I hate them. Yes.
So, in like theory, should there be like no radioactive waste coming out of this? Like if there's no meltdown or no air or anything?
Well, yes and no. When everything is working correctly, there is an accumulation of radioactive waste, the fuel rods, and by the way, all the plumbing, when you got to change the plumbing, it's radioactive. And you know, those control rods, they'll become radioactive waste. So you are building up radioactive waste.
But you're not releasing it.
But you're not releasing it, that's right. That's right. So until you open the containment structure and move this to Jay's house, there's no release of radioactivity when this is working right. And if we want to get hyper nerdy about this, and somebody's going to call me out for saying no release, fine. There's an exceptionally irrelevant release. If you're outside the containment structure, nothing's 100%, right? So it contains 99 point a bunch of nines of the radioactivity. So yeah, there is a little release, but pretty irrelevant. Who else? We're getting somewhere here. I'm almost done now with the. Yeah.
Yeah, you know how you said there hasn't been any building of a nuclear power plant since whenever, a long time ago.
We're in the U.S. anyway. Yeah.
Isn't there like one unfinished one in like San Diego where like some of the parts were bad, so they stopped building it or something?
I don't know about that, but near San Diego, there's one in San Clemente called the San Onofre power plant. It's right by San Onofre State Park. The San Onofre one was just decommissioned in 2014. And they're forced to shut it down because it's not aging very gracefully. Is that what you're thinking about, maybe? There must be others, I don't know, but I don't know. All right. Now, in your assignment 7.5, you probably have a big jumble of vocabulary that I haven't answered, but now you can answer all sorts of stuff. this lingo bouncing around in the unit is now a lot easier, I hope, to talk about. First of all, this is usually called a PWR, pressurized water reactor. You understand why it's pressurized. To keep the coolant from evaporating and taking away the heat, so you can hold more heat. Pressurized water reactor so that the reactor gets hot. Like a pressure cooker. James Bell, put your phone away. And I'm going to start reminding you on the daily because I'm kind of cracking down on this. It's not personal, I'm doing it to everybody. I'm trying. Usually we use what's called light water. It's just plain old H2O. Whenever you hear a light water reactor, that just means a water reactor. Like light water reactor is like water. Like that's light water. All water is light water. But that is opposed to something which is different. You have to call it light because there's this thing called heavy water. And now we get into a lot of details that a lot of you might find confusing. So if you want to skip the nerd talk, heavy water is a coolant that also moderates.
So it's like water with boron in it?
Conceptually, it's like that.
Or water with some other thing in it?
But here's what the other thing is. Do you guys remember that hydrogen has an average atomic mass of about 1 because of the proton with an electron? We talk about that? Hydrogen is a proton with an electron? There is an isotope of hydrogen called H2, which has a neutron, proton, neutron, and electron. It's called, please look up, H2. And if you make that into water, it's H2O. That's heavy water. Apparently because the hydrogens have neutrons, the oxygen can also carry more neutrons. I don't understand what I don't know. Somehow it's a moderator.
And stable.
Yeah. So, they're called pressurized water reactors. Usually it's light water, which is AKA water. But there is this thing called heavy water, which is water made of H2. That's called deuterium. I'm not underlining it because, frankly, I don't know how many of you will need that for the AP test. But science nerds, rejoice. It is both coolant and moderator. It's made of deuterium. Apparently, the Canadians run all of their reactors this way, and that's some sort of a safety issue. Like if the control rods aren't there, the coolant is still slowing the reaction. By the way, you need science nerds that are really science nerds, you need the deuterium to better manage the decay of the ingredients. So for a breeder reactor, I think it's mandatory that it be deuterium. Back to normal class. There's this stuff called spent fuel. That's what happens when the 235 is all transformed. The 235 is all transformed. So if you look at those numbers up there, you'll notice we were 97.3, but now that 3% 235, that's become the crazy fission stuff. And interestingly, the 238 has gotten a little bit lighter. Some of that went downhill, but some of it went uphill to plutonium. I know that this might seem like a bunch of details that are hard to keep track of, but I swear we're almost done with the details. Stay with me. Spent fuel rods have a bunch of radioactive waste. Remember, it's super radioactive. It's the most radioactive thing that we've talked about because those smaller atoms can't hold all those extra neutrons. Remember that? So they're going to keep spitting off neutrons. Very radioactive. That's very dangerous. Okay, that's the radioactive waste part. But look, plutonium should be impossible on Earth. I keep alluding to these mysterious attractive forces inside the nucleus. Whoa. I keep talking about how they're kind of like gravity and kind of like magnets, but they're not gravity and they're not magnets. Ooh.
Magic.
And I don't really understand how the F any of this crap works, but there are science nerds who get it, and apparently, in all of that chaos of splitting atoms and little pieces and the Legos hitting the ground and all that funk, by accident, sometimes you make an even bigger atom. A proton or two gets stuck. And you build plutonium, and the reason that's important is because plutonium is a really special fuel. For one thing, it makes hell of good bombs. But for another thing, it makes a very, very good nuclear reactor fuel. So, back to the notes you need to have. Spent fuel is used up fuel. It has highly radioactive, because the little atoms can't hold all those neutrons. And spent fuel also has a little plutonium. Yeah.
Would you say it was good for besides bombs?
Nuclear fuel. In a separate type of reaction, you can recycle that into a fuel. Yeah.
So for the fuel rods, do we want 235 or 238?
We want the 235.
235.
The 238 can be used for stuff. We talk about bunker busting, a projectile, heavy frying pan. Now, there's two strategies for how you use your reactors. One of these is new vocab, one is not. Please look up. They're called burner versus breeder reactors. Burners use up the energy. Use up the fuel. Breeders structure the fuel to make something else useful. That's a breeder reactor. You get a bunch of nerds and a lot of extra plumbing. That requires a lot of extra engineering, but you can make the spent fuel into something else you want to use. No, just put it away, actually. Next, you remember we were talking about these fuel rods, these assemblies of the uranium that are like literally like metal pipes and they get very, very hot. But you know, they can get too hot and they melt and that's scary. So there's these things called pebble bed reactors where the uranium is rolled up into little tiny pebbles sitting on a screen, and so that the airflow passing through those pebbles will cool them off. In other words, pebble beds are inherently safe. They are passively safe. They dissipate the heat so quickly that in an accident they cannot melt down. At least this is the hope. Yeah.
So why aren't we making more nuclear power plants with this if we know that it's really safe?
So A, they're not quite as efficient. You know, if they don't heat up enough, then it's like, well, they don't heat up enough. B, we are. There's a lot of what we call passive safety measures that are becoming common. We in the United States, we stopped building these after we had a partial meltdown near a big city. So we're like, you know what, I want to back off on this. And the US hasn't really gotten into the nuclear thing since then. But in other countries where the engineering has continued, they've been making newer reactors that have, for example, control rods that require a human to keep them out. So when people evacuate, or if they don't show up, or if a terrorist blocks the gate, the control rods without a human there will fall into place and take away neutrons by default. It would seem like a pretty good idea, right? Like, you've got to have somebody there to press the button, or by default, it's safe. There's another one that they do, I think, in Canada, where all of these are up a level on top of a giant pool of coolant. So if you have a meltdown, it falls into a pool of coolant. And there are a gazillion other things that I just don't know about because I don't know about them. But there is a trend worldwide to make them what's called inherently safe or passively safe, which means that the automatic response is additional safety, that they're built to auto-correct disaster. Would anyone else like to ask me anything about any of these words or these diagrams? Because I'm kind of ready to call it quits on the nuclear stuff. Yeah?
What did you say a burner reactor does?
Burner reactors use up fuel and just make waste. Breeder reactors sort of structure the waste into being something you can use. You know, like when you're building a house, there's like the people that will just throw all the leftover parts into the dumpster. And then there's the people that will like chop up the scrap wood to make firewood. Burner, breeder. Make your waste into something that you can use in another manner. Yeah?
Where does that coolant go after it cools down the reactor core?
Okay. The coolant is the heat exchange liquid. This is continuous.
So if you keep putting in cold water, would it like fill up?
You're not adding any water. The primary cycle is sealed. So this is hot water inside of a pipe that comes back cold.
What was that other pipe going in there?
So we have separate cycles, and I hope everybody heard his questions. If you don't understand that, you are screwed, bro. I'm glad you asked. Primary cycle is a closed loop where the water moves but doesn't leave. All that leaves is heat carried by water, which transfers to a separate cycle of water that comes in cold and takes away the steam. So the heat is moving, but this water is contained. That's why it's always in a containment structure. Radioactive stuff should not be leaving. Understand what I'm saying?
Yeah.
The secondary cycle is separate water. It's not radioactive water. You could go have a sauna in there if it wasn't loud and too hot. Who else? Yeah.
How does the heat exchanger change it from hot to cold?
It transfers the temperature. If I drop this into a pot of hot water, this will get warmer, the hot water will get colder, right? Like if you put a huge pot of freshly boiled soup into your freezer, that's going to add a bunch of heat. It's going to take a while for it to cool down, right? Heat exchange goes two ways. When my wife is really cold and she gets in bed at night, her feet will usually find a way to my feet where I'm comfortably warm. Her freaking icicle, because she doesn't have a heart, like her icicle feet will chill my leg, right? So there's heat transfer going on. Her feet are getting warmer at my expense. Damn it. Right? So this is a two-way street. Hot water is giving its heat away. It's radiating heat, and so it comes back cold because that heat's gone somewhere. That's that countercurrent flow thing, where the coldest water meets the barely warm, and where the hottest water meets the hottest heat exchange. So we're transferring the heat and steam. Yes? Yes.
So when you talk about burner versus breeder, what's an example of breeder?
The U.S. doesn't have any that I'm aware of. I believe France and maybe Germany, I don't know. Some of those smart European countries, they're the only ones that are doing this. And so they intentionally, they've got a bunch of plumbing in here that like adds gases so that in all that chaos of like bing, 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 and like crazy radioactivity, who the hell knows what is going on with the fission, they're like, in the middle of all that, let's add a few ingredients and we'll get an omelet. And so they are guiding the decay to make more plutonium, because plutonium is very valuable. As far as I know, they only make plutonium. Plutonium is impossible on Earth, so if you can make it, that's really handy for bombing your neighbors and stuff like that. Yes. Yes.
So what cold water goes in? Is it just like lakes or like ocean water?
Usually these are near rivers or near coastlines.
Maybe you just use ocean water and then the steam takes away the like salt and then you could use that as clean water?
To desalinate while we're at it, I think that you.
Because if
I
you
don't know.
boil water like salt water, it's drinkable.
Yeah. I imagine that theoretically that would be possible, but it's probably not the best way to do either of the jobs. Like salt water is not a good thing to be boiling, and then salt water and all the plumbing, the turbines, still some salt aerosolized. I'm going to guess that there's probably better ways to do both of those jobs, but I don't know, maybe you could. Get on that. Yeah.
So you said you drew the third cycle kind of wrong. So what would it look like with countercurrent flow?
Red on the bottom, blue on the top.
Huh?
Red on the bottom, blue on the top.
Okay. So you'd have like the cool lake water coming from the
Above.
top. Okay.
It's just the direction of water is probably relevant to the concept here. And technically, for condensing, I wonder if this isn't better. No, it's probably not better. Who else? We done? No more nuclear? What the AP test will do is they won't label one, or they won't label any, and they'll be like, question number 1, what is A? And you get 5 choices. Question number 2, what is B? And you get like 5 choices. Question number 3, what happens at C? And you'll have to like describe, one of those 5 descriptions. Yeah.
Will nuclear be one of them?
Yes. Please notice the river provides the cold water, and to dissipate the low quality heat energy, you have those giant towers. When you see them as radioactive on The Simpsons, Matt Groening was lying about that. They are not radioactive. It's just plain old steam. Birds love nesting in those. It's okay for them.
That's
Yeah.
Wait, why is the steam coming out if we are probably contained?
Because there's many transformations of energy. We're getting colder and colder and colder as we go. We got to dissipate heat. In any transformation of energy, some quality is lost.
Okay, so
there's 2 types of steam, right? There's really effing hot pressurized steam that's like a jet of pressure venting. That was in a turbine. But in order to condense that back to cold water, which you have to keep in the supply chain, then you've got to make a separate, this is just to shed heat. It's called the heat dump cycle. Because it's just there, like now that we're down to like barely usable heat energy, we've got to get it out of the system. You can't have the heat backing up. Yeah.
So in this particular photo, where is the containment structure? Because those are the big towers that have steam going out of them. Where's the
There are 2 round buildings that look like grain silos. Please look up. Those are the containment structures. So reactor core 1, reactor core 2, electrical generation, heat dumping. And by the way, if you look there, you can see that you can like walk through in the bottom there. They take like school field trips. You just walk in and go like, oh neat. Like it's just a big tube. Yeah.
What's inside the cooling tower? Is it just like
Nothing. They're just open air. They're literally like convection current builders. So it's open air at the bottom, and they spray in the hot water and just like let it mist in there. And then because that's hot, it generates this current that forces it to evaporate. So if you spray hot water into a tube that's open at the bottom, you'll get steam out of it.
Why are they so big then, if you could do that?
Because they're dialed to the amount of energy you have to dump. Another way to look at that is, that much steam is how much energy you're getting out of that tiny reactor core. Anybody else? At San Onofre, the one that many of you will see and remember forever, there are 2 reactor cores, they're both contained. There's the electrical generation stuff over there, and all of this rusty stuff along the beach, that's just for the hot water in and out. We love to put nuclear reactors near the ocean because we have an eternal supply of cold water and a great place to dump the heat. Of course, that sucks if you're building these on the ring of fire, like highly tectonic active areas, like Morro Bay or San Onofre, because we've got this thing called the San Andreas Fault running through the middle of California. And as we learned from Fukushima, there are occasionally earthquakes. Huh.
No.
Communist. Yeah.
Is heavy water the only water that can be used for this?
No, they're both possible. Light water and heavy water can both be used in the first cycle.
Is salt water heavy water?
Salt water is not heavy water. Heavy water is the heavy isotope of hydrogen, too. Salt water is not heavy water. Salt water is salt water. Who else? So there's this place called 3 Mile Island. You don't necessarily have to copy all this, but it's good to know what happened. In the second cycle, there was a leak. Please look up. You don't need to copy this, so please look up. Imagine, like, over here by the E, there's a leak. So some of this cold water is getting out. That means, please look up, that this water is going to eventually get used up, right? Turn to steam but not be replaced. You know what I'm saying by that?
Yeah.
Because it turns to steam and doesn't get replaced, then you don't have enough space to shed the heat. So what happens to the water going back?
Hot.
Right. And if you're bringing in hot coolant, then that's not going to work so well. So the pressurized part, the primary cycle, gets hotter and hotter and hotter until it really, you know, like that pressure venting system on a pressure cooker? Well, this reactor core got so hot that it and released the pressure vent, but that thing got stuck in the open position. So because it got stuck in the open position, all the coolant vented, and then you have a dry core, which is pretty much disaster time. Because with nothing to take away the heat, the metal just goes like, and it gets to be like unbelievable lava hot. So it allowed heat to build in the reactor core, and through all of this, people in the control center were like, oh, pretty red lights everywhere, it's like Christmas. And there was just like, like alarms going off and like blinking lights, and all the things are all like pinning on the right, and it was like, I wonder what all this means. So there was both a combination of mechanical failure, which is always going to happen, and then the redundancies, and then there was like a stack up of mechanical failures, like a pressure thing. Should have been like, okay, everybody, just cool things down, and we'll go out a little bit more, and we'll fix the leak, no big deal. Like, all this stuff happens all the time. But there was a number of mechanical failures, and then the humans were, like, asleep at the wheel. And so inside of that reactor, that pressure valve got stuck in the open position, and the reactor core, nobody's actually been able to look at it because you can't open it because it's like, you know, a gigantic ball of death. So nobody's actually looked inside, but the theory of what happened when you run the simulation is that all of the uranium melts into this stuff that starts to pour through. to the bottom, and it basically just filled up the bottom of the reactor core with molten high-level radioactive waste.
Nice.
And you know, the containment structure never leaked, supposedly. So the radioactive stuff never got out, supposedly. There was a bunch of radioactive steam, primary radioactive. You know what I'm saying? The coolant, this stuff, what's radioactive, that evaporated in the containment structure. So there's no doubt that the containment structure was full of radioactive. But humans were able to turn on the water and cool things down and drop in enough control rods to stop the reactions. And supposedly everything was under control. But a bunch of the neighbors have reported that there was some measure of radioactivity seen in the communities nearby, and there are supposedly maps of cancer clustering around 3 Mile Island. I take no opinion on whose facts are which. I don't know. I'm not big on conspiracy theories, but one group of people says no big deal. It was all contained. We had a close call, but it was just a close call. Another group of people says, wait a minute, my mommy's dying of cancer, it's probably your fault. And so there's this like, maybe a bunch of tin hat conspiracy wackos, or maybe it's a real conspiracy. I don't know. About 3 Mile Island. What we do know is that the containment structure was basically, according to what I have heard so far, it was intact. Yeah.
So is it just like sitting there now?
Yeah. I believe that one of the reactors still operates, and if I'm not mistaken, the other one's also working. They removed the radioactive core and have put it in somebody's swimming pool. If you guys want to hear the most spectacular comedy in the history of film, there's a movie about the meltdown of a nuclear reactor. They showed a little snippet of it in the movie at the beginning of our unit. Do you guys remember at the movie that you saw on the first day of the unit?
Yeah.
There was like, it's not called the Manhattan Project, but it's something to do with Manhattan. Anyway, that movie was in theaters when 3 Mile Island happened. So imagine you go watch a movie about a nuclear meltdown, which the public was really nervous about. In the mid-1970s, people were like really, this was like a big topic. By now, we're just kind of over it. But in the 1970s, this was like a major social issue. People go watch this movie about a nuclear meltdown, and they're like, wow, I'm glad that was just a movie. And they walk outside, and there's like sirens and people running through the streets and screaming about the meltdown at the reactor. Like, you go watch an alien movie and you come outside and there's aliens. Like, to me, that sounds like the most unbelievably horrific mental experiment in the history of humanity. That there were actually people leaving the theater at 3 Mile, or near 3 Mile Island when the 3 Mile Island reactor went off. I guess I'm the only one that sees the excitement about this. Secondly, there was the worst radioactive event in the history of the world. To put this into perspective, this was roughly the radioactivity content of 100 Hiroshimas. There was a very special detail about the USSR, the Republic of the United Soviet States. Both Ukraine and Belarus were all part of this, with Russia and a bunch of other places I can't remember. The USSR was struggling to balance poor communities with wealthy communities. It was a very, very big republic. And so they kind of cut some corners on design and certain things historically. And so check this out. They used cold water to cool the reactor, and watch my finger, and they used coolant steam for the turbine. The turbine was in the containment structure. They only had one cycle, not two. Ever see what I mean by that? This is 2 cycles. They used primary steam for the turbine, which is pretty sketchy because.
Wait, and then they just let it out like.
No, and then they recondensed it. So they had this part inside here, and the steam was generated by the core. So they only had one heat exchange system. There was radioactive steam for the turbines, and the supply of coolant failed. So the story is really simple. When you lose the coolant, you get too much heat, and it wasn't controlled in time. And just so that we're all on the same page, you never want to see that. The heat was so extreme that when the containment structure fell in, most of it just vaporized. The core is still sinking its way through the Earth's crust right now. It's just been covered up with sand and then a concrete containment structure. And now that people notice that containment structure is crumbling, the European Union is scrambling to build a multi-hundreds of millions of dollars new containment structure. They have to build it over here and then build 2 train tracks to slide it over. And entomb the waste. They tried helicopters to drop in sand. They tried sprayers to squirt in water. There's the very simple design. And entire communities had to be evacuated. The giant spreading cloud of gnarliness looks sort of like this. The simulation takes a few minutes. You can see where Chernobyl is. That was the 12-hour mark. This is the 24-hour mark. But at some point, those emissions reach the high elevation, and high elevations, they move very, very fast. So after one day, you kind of got up there. After a day and a half, things are starting to spread more quickly. But there's this moment when you reach the 2nd or 3rd days that some radioactivity gets into the upper atmosphere, and then jet streams just go and throw the radioactivity all over the planet. They measured radioactivity in Buenos Aires and Cape Town and Auckland. It took about 12 hours for some radioactivity to reach New York. You'll notice that the overall dosage for many areas near there was pretty exceptional. It's been almost a week at this point. And radioactivity was still going up, not down in the lower atmosphere. When you see the global map of this, it's pretty amazing what happens in the upper atmosphere. Yeah?
So a lot of times it shows radioactivity going over an area and then leaving.
Yeah.
Does that just completely remove all traces of it?
Nothing removes all traces of it, but it does move. So you've seen clouds move, right? Funny thing about radioactivity is it'll travel like that cloud, but as it goes, it changes things. Radioactivity is kind of like ink moving through water. Anything in that water will be stained by the ink.